Hi all, let's go ahead and look at the section 7.3, which is going to go over the trigonometric substitution problems. I have a little chart here that I think will be helpful as far as deciding what to do in the first step in each case. Now, here I say to begin with that it's the root in the integral. Kind of take that with a grain of salt. In most of the easy problems, you're going to see square roots and stuff in there. It's not always a square root, and in fact, it's not always even a root. It could be a group to the second power, a group to the third power. But what the main thing that we're going to be looking for is anytime you have a constant squared minus a variable squared. It is often inside of a square root, but it doesn't have to be. But anytime you have a constant squared minus a variable squared, you're going to set up the trigonometric substitution to let that variable, x in this case, it's not always x, but if you see an a squared minus x squared, then you're going to let x equal a times the sine of theta. Please notice you're taking the square root of each of these terms over here, so it's just the square root of the variable is equal to the square root of whatever that constant is times the sine of theta. And then whenever you make this trigonometric substitution, I guarantee you're going to be using an identity to say that 1 minus sine squared is equal to cosine squared. And then it's going to set up a nice substitution in your problem. Anytime you see a constant squared plus a variable squared, you're going to let that variable, notice again we're taking the square root of both the variable and the constant here, we're going to let that variable equal a tangent theta, and then the identity that you're going to end up using is going to be 1 plus tangent squared theta is equal to secant squared theta. Well, the other scenario, and there's only these three scenarios here, the other scenario is when you have a variable squared minus a constant squared. Anytime that's the case, you're going to say, well, all I need to do is let that variable equal the constant times the secant of theta, and then the trig substitution that comes into play is secant squared theta minus 1 is equal to tangent squared theta. Now, that probably seems a bit strange here at first. You're like, well, how am I going to use that in problems? Let's look at a problem. So I've went ahead and worked out a few problems that I think will help us get this concept here. So the first one here that I want to look at with you, the problem here is 1 is equal to, 1 is the integral of x squared over the square root of 9 minus x squared, and we're trying to integrate that with respect to x. Absolutely the first thing I do in this problem is I look at that denominator that has the square root and I notice, hey, that's a squared minus x squared. That puts me into the first format here, so notice what I did. A squared is 9 in this case, so a would be 3, so I need to let x equal 3 sine theta. Please notice how I'm just using this very first trig identity up here, or sorry, trig substitution, and then I will use that trig identity in a minute. So all I need to do in this problem is to let x equal 3 sine theta. But if I let x equal 3 sine theta, I also need to figure out what dx is. So I take the derivative of both sides. Derivative of x is dx. Derivative of 3 sine theta is going to be 3 cosine theta with respect to theta. Okay, so now I come down here. This is the integral of, notice that numerator is different. Well, it's different because the numerator was x squared. I also had to go back here and say, well, if x is equal to 3 sine theta, then x squared is 3 sine theta quantity squared, which is 9 sine squared theta. So I have my numerator in there. My denominator, well, actually, first I'll talk about my dx. My dx became 3 cosine theta d theta. My denominator became exactly what I needed it to be. It was the square root of 9 minus 9 sine squared theta. Well, I already know that I'm going to use this identity there. So from this step to this step, what happened? Well, all I've done is I've said that that denominator is the same thing as the square root of 9 times 1 minus sine squared. Well, the square root of 9 times 1 minus sine squared is the same thing as the square root of 9 cosine squared theta. But then I know that that square root of 9 cosine squared theta is going to become the 3 cosine theta, which is going to cancel with the 3 cosine theta that I was multiplying by. So what I'm saying, from this step to the other, right here, this denominator, that's equal to the square root of 9 cosine squared theta, which becomes 3 cosine theta. And notice that 3 cosine theta is going to cancel with the 3 cosine theta that I was multiplying by in there. So then my next step simplifies gorgeously. I can say from here to here, all I'm doing is I'm canceling out the 3 cosine thetas, I'm bringing out the factor of 9, and then I have the integral of sine squared theta. So I can say, well, okay, now in order to do that, from this step to this step, I'm using my power reduction formula, which, please remember, again, we say, well, the sine of 2 theta, that's just going to be 1/2 times the group 1 minus the cosine of 2 theta. So at that point, I can say, well, okay, then this is going to be 9 over 2. The 1/2 comes out with a 9 on the integral of 1 minus cosine 2 theta. And at that point, it's easy to integrate. The integral of 1 with respect to theta is theta, and the integral of the cosine of 2 theta is going to be the sine of 2 theta over 2. So I get minus 1/2 sine of 2 theta. And then when I went from this step to this step, I went ahead and solved for what the theta was in this problem, but then I had to use yet another trig identity here because I don't know how to deal with the 2 theta. So from this step to this step, what I did is I said the sine of 2 theta is 2 sine theta cosine theta. Okay, so now notice what happened. We know in our original problem x is equal to 3 sine theta. So we know that the sine of theta can be called x over 3. Well, if I'm trying to solve for theta, then theta is just when we take the inverse sine of both sides, and theta would be the inverse sine of x over 3. So I'll get 9 over 2, inverse sine of x over 3, and then minus 1/2, and then that 1/2 is going to be multiplying the 2 sine theta cosine theta. Of course, at that point, I have to cancel those two factors, but then it becomes the step of how do I solve for the sine of theta and the cosine theta. And that's where I draw a trig triangle given the original relationship. Notice I just brought that down here and I said x is equal to 3 sine theta, so x over 3 is the sine of theta. We know that the sine of theta is the ratio of the opposite to the hypotenuse within a right triangle. So knowing that the sine of theta is x over 3 allows me to draw a right trig triangle, and drawing in the angle theta and then saying the side opposite that angle is x, the hypotenuse is 3. And so now the adjacent side has to be the square root of the square of the hypotenuse minus the other side squared, so 9 minus x squared in there. Now, one of the things on your trig triangle that I always want you to remember, the expression from the original problem must pop up in that trig triangle. If it's not, you're doing something wrong. So I knew as soon as I set up that trig triangle, I would see a 9 minus x squared in there. And I do, the square root of 9 minus x squared. Okay, so now I go to my final problem and I'll say I already had the inverse sine of x over 3. I've just multiplied it by 9 over 2. The 1/2 and the 2 canceled. I'd have 9 over 2. But then notice I'd have a sine theta cosine theta. Well, sine of theta is where the x over 3 is coming from. The cosine of theta is where the square root of 9 minus x squared over 3 is coming from. And ooh, notice I didn't bring my factor of 9 over 2 to the second one, so I canceled out those two. But this also has to have a factor of times 9 over 2, I'll put down there, because it has to be distributed in that term as well. And so then in my final answer, where I have multiplied by 3 times 3 to get to the 9 here, we know that this denominator should be a 2. This 9 is going to cancel with the factor of 9 in the numerator, and I would get a 2 down there. It's not good when I have to correct myself. Yeesh. So now, up next, when we look at the second problem here. So I want you to make sure you see that we're doing all the different types of problems here. We need to be able to see how to do a sine substitution, a tangent substitution, and a secant substitution. You do a sine substitution anytime you see a constant squared minus a variable squared. Well, okay, when do you do a tangent substitution? Whenever you see a constant squared plus a variable squared. So now notice on my number 2 here, I have the integral of 1 over 4 plus x squared, and I've already done something other than a square root. It's the square root cubed, or the 3 over 2 power. So I automatically have to recognize that 4 plus x squared is a squared plus x squared. A is going to be 2. So I let x equal 2 tangent theta here. Well, if x is equal to 2 tangent theta, then dx is its derivative, which is going to be 2 secant squared theta d theta. So now I come down and I work with that 4 plus x squared to the 3 over 2. I really think it's wise to actually, instead of like I did in the last problem, where I just put the 9 minus 9 sine squared already into the integral and had to try to simplify it to think of how to get this step, it's probably best if you do like I did here, and instead of going ahead and plugging it in the integral, figure out what's going on with that relationship before you work the integration problem. So here I'm just saying, well, what's happening to that 4 plus x squared to the 3 over 2? I know that I'm letting x squared, or I know that I'm letting x equal 2 tangent theta, which means x squared is 4 tangent squared theta. I know in that expression I would factor, or I could factor a 4 out, leaving 1 plus tangent squared. And then you'll see up here in my chart, I said every time you use this substitution, you would be using the identity 1 plus tangent squared is secant squared. Well, we are. So now I see that 1 plus tangent squared is going to be secant squared. So the inside portion is 4 secant squared theta. But then I'm raising that to the 3 over 2 power. Well, I know secant raised to the 3 over 2 power, or sorry, secant squared raised to the 3 over 2 power is just going to be secant cubed. 4 raised to the 3 over 2 power, that's just the square root of 4, which is 2, and then 2 cubed, 8. So I get an 8 secant cubed theta out of that denominator. Now I go back into my integration problem. I say, so the original problem is equal to my numerator. Where did that come from? I decided to go ahead and put the dx up in the numerator. Remember that dx is always implied to be in the numerator. So my numerator became 2 secant squared theta d theta. My denominator, the 8 secant cubed theta. Now at this point, I can say, well, the 2 over 8 is going to come out as a 1/4. And if I have secant squared over secant cubed, I know I have 1 over secant in there. But if you have a secant in the denominator, it's better just to say, well, that's the same thing as a cosine in the numerator. So that's what I did. Now I'm integrating the cosine with respect to theta. We know that's easy. The integral of the cosine is just going to take me back to the sine function. So I get 1/4 sine of theta plus c. But now your original problem was in terms of x, so we can't have an answer in terms of theta. That's where the trig triangle comes in handy. So you say the original trigonometric substitution that you use is always used to design your trig triangle here. This trig triangle in this case, I said x is equal to 2 tangent theta, which means x over 2 is the tangent of theta. So I'm looking at this and saying, okay, that means here that theta is going to be the angle in a trig triangle in which the side opposite theta is x, the side adjacent to theta is 2, which means your hypotenuse has to be the square root of the opposite side squared plus the adjacent side squared, x squared plus 2 squared, x squared plus 4. I kind of wish here I would have went ahead and put 4 plus x squared. Same thing, obviously, x squared plus 4 and 4 plus x squared. But that would just solidify the fact that it's always the same as the original expression in the problem. But notice that is what I did over here in my answer. I said 1/4 and then the sine of theta. Well, the sine of theta, I look at theta in my trig triangle and say, well, the sine of theta would be opposite over hypotenuse. That's where I'm getting the x over the square root of x squared plus 4, or better written in this case as the square root of 4 plus x squared. So I get 1/4 times that quotient plus c, final answer. Of course, you could go ahead and distribute the 4 in there and not have that fraction. I think I would even prefer, while that answer is fine, I'd prefer this, x over 4 on the root of 4 plus x squared plus c, QED. Now, you're thinking, well, that was a fun problem. It was. Let's go ahead and look at another one. Again, I want to make sure you're able to do all of these different types of substitutions. So we've done a sine substitution and we've done a tangent substitution. Next up, secant substitution. So before I even show you this problem, you should be thinking, okay, every time we do a secant substitution, it's going to be because we have x squared minus a squared in there. Well, notice my problem for number 3, I have the square root of x squared minus 16 all over x, and I'm trying to integrate that with respect to x. The instant I see that x squared minus 16, I should be thinking, well, okay, that's x squared minus a squared, where a is 4. So I will let x equal 4 secant theta. So now, if x is equal to 4 secant theta, then dx is going to be the derivative of secant is secant tangent, so 4 secant theta tangent theta d theta. Now, in this case, I went ahead and just put it back into the problem. I kind of prefer it where if we simplify before going into the integral, but this is okay too. So I have the square root of x squared minus 16 becomes the square root of 16 secant squared theta minus 16 all over x, which is my 4 secant theta. And then notice the dx, that's where I rewrote in its place the 4 secant theta tangent theta d theta. Now, I set this equal to over here. I said, well, okay, a lot of stuff is going to cancel. The 4 secant theta cancels with the denominator in this term here. We know that this square root, let me show you that over here, that square root of 16 secant squared theta minus 16, what I didn't show here is what happened to that. That would be 16 times secant squared theta minus 1. Well, you know secant squared theta minus 1 is tangent squared theta. So this is the square root of 16 tangent squared theta. You say, oh, okay, now I can take the square root of both parts. Square root of 16 is 4, square root of tangent squared is tangent. Gorgeousness. So now, please notice what you would have remaining in your problem. The 4 secant theta cancels in the denominator in this term, but I would have left this tangent theta, and I know all that numerator up here becomes 4 tangent theta, so I would have 4 tangent theta quantity squared, which is where this comes from. Okay, so now I'll go ahead and go to my next page here. So I've got that 4 tangent squared theta. When I'm thinking 4 tangent squared theta, I went ahead and rewrote it. The reason I did is because the integral of the tangent function, it's not impossible, it just requires some substitution. But rather than do that, I kept with the trig identity and said, well, tangent squared theta is just going to be equal to its Pythagorean identity, secant squared theta minus 1. So whenever I did this, I said, well, that makes it easy to integrate because I know that the integral of secant squared, since the derivative of tangent is secant squared, the integral of secant squared just gives me the tangent function. And then, of course, the integral of 1 with respect to theta is just theta. And we add our constant of integration. But now that you're at this point, you say, okay, this is the point in the problem where we need to put our answer back in terms of x. Well, in order to do that, you use your original relationship. X is equal to 4 secant theta. X over 4 is equal to the secant of theta. So we can say that, or we can say, well, the cosine of theta is the reciprocal of that, and the reciprocal being, in this case, 4 over x. So I can say, well, the adjacent side is 4, the hypotenuse here is x, and I have my square root of x squared minus 16 in here as well. So now I'd go back to my problem and I'll say, okay, once I have my trig triangle defined with the adjacent side being 4, hypotenuse x, and the opposite side, the square root of the hypotenuse squared minus the other side squared. And please remember, every time I said that the relationship from the original problem must pop up in the trig triangle. So if you would have done a trig triangle and didn't see that x squared minus 16 in there, you'd know you'd have to be wrong. But we're not wrong. So now I go over here in my problem and I'll say, okay, 4 times the tangent of theta. That's opposite over adjacent minus 4 theta. I don't even need the trig triangle for that. You could look at either one of these two expressions. It doesn't matter which one you use. In fact, I used inverse cosine just because it makes a lot more sense to people, but it might be better to stick with the secant just because the original problem had a secant substitution. So you could either say let theta equal the inverse secant of x over 4, or let theta equal the inverse cosine of 4 over x. Same thing either way. In this manner, I stuck with the inverse cosine. One's not really better than the other. And then I added my constant of integration, done with that one. So now you're thinking, well, that was a cool problem. How can I make these problems even more cool? Well, the way that you can make any problem more cool is to force you to have to do some gorgeous algebra in there. So the algebra in this one that I'm wanting you to remember is the completing the square. The completing the square, where you say a perfect square trinomial is always going to be x squared plus 2 times the a times the c term x plus your c squared term in there. So whenever I'm trying to create a perfect square trinomial out of one like this, and first of all, you have to recognize the necessity for it. In number 4, the thing that differentiates it from the ones earlier is that you don't see a variable squared plus a constant squared. Well, that's problematic. So what I want to go ahead and do is to force that to happen by completing the square on this trinomial. So I go ahead and I say, well, okay, I'm going to gather the two terms of x and I'll push the 7 to the outside of that group. Now I think about what I need on the inside of that trinomial to make that a perfect square trinomial. Please remember, you always need whatever the coefficient of x is. We say b, you always need b over 2 quantity squared. So 4 over 2 is 2, 2 squared is 4. That's why I put that 4 there. But that 4 was not initially there at the beginning of the problem, so I have to make up for that by, if I'm going to add 4 to the inside of the group, I subtract 4 on the outside of the group. So I know that x squared plus 4x plus 7, it's the same thing as x plus 2 quantity squared plus 3. So now I can say, okay, I'm going to do a U-Substitution and let U equal x plus 2. If I do, du is just dx, so that's an easy substitution to make, and it simplifies my problem to this. So the u squared is taking the place of x plus 2, and then I would have the plus 3. This problem becomes this. Now, I have forced it to look like number 2 earlier, where you have a variable squared plus a constant squared. But this time, the constant's not a perfect square. No big deal. You say if a squared is equal to 3, then a is the root of 3. So I need to let u equal the root of 3 tangent theta in this problem. Now when I do that, du is going to be the root of 3 secant squared theta, d theta, derivative of tangent theta there. Now I go back into my problem and I start plugging things in. I know that du is just the square root of 3 secant squared theta d theta. My denominator becomes the square root of u squared plus 3. In this case, remember, u squared plus 3 is going to become the square root of 3 tangent theta quantity squared, which would be 3 tangent theta squared, and then plus 3. And you say, well, the whole point for doing that was that I could write this as 3 times tangent squared theta plus 1. We always use this trig identity in these problems. Tangent squared theta plus 1, we know that that's just going to be secant squared theta. So that's what I tried to show here. We have in that square root, it becomes the square root of 3 times tangent squared theta plus 1, which is just 3 secant squared theta down there. But then the square root of that, the square root of secant squared theta is just secant theta, which is why I have a secant theta in my denominator. My numerator already had the secant squared. What happened to the square root of 3's? Well, they just canceled each other out. You had a square root of 3 as a factor in your numerator and denominator. They cancel. So then secant squared over secant just gives me secant to the first. That's one of our formulas that's a little bit more difficult to take the derivative by hand. We did take the derivative by hand in class, but this is one that it's best left to the rules in the back. So you go to your integration table, number 13. The integral of the secant function is the natural log of secant plus tangent plus c. Now once you get to that part, we need to see how to get to our final answer in terms of x. So first I'm going to take my answer theta and put it into terms of u. So I know that u is equal to the square root of 3 tangent theta, which means u divided by the root of 3 is the tangent of theta. I draw my trig triangle and I say, okay, if the tangent of theta is u over the root of 3, opposite is u, the adjacent is the root of 3, and the hypotenuse is the opposite side squared plus the adjacent side squared, all inside of a square root. So I can say, okay, trig triangle defined. I go back to my problem. Secant of theta. Secant is the reciprocal of cosine. Cosine would be adjacent over hypotenuse, so secant is hypotenuse over adjacent. That's where that came from. The square root of u squared plus 3 over the square root of 3 plus, now I can say, for my next term, the tangent of theta. Well, that's opposite over adjacent. Opposite over adjacent here. I had to add in my constant of integration. The only thing I have to do from that point is go ahead and back substitute. We know that u is equal to x plus 2. So I can say, well, then u squared is x plus 2 times x plus 2, which we know is our x squared plus 4x plus 4. So you can say, well, that's x squared plus 4x plus 4 plus 3. And that just takes me back to the original x squared plus 4x plus 7. So the u squared plus 3 was used to substitute the x squared plus 4x plus 7. Plug that in over the root of 3. U is just x plus 2 over the root of 3. And then we put in our constant of integration. Now, from this step to this step, I really need to make sure that you get what I'm doing here, because this is important on achieve. Achieve will say that you need to make sure C absorbs as much as possible. It doesn't want any other constant in the problem that's not part of the C. So I could go ahead, and I'm going to show an intermediate step here. This natural log would simplify to be the natural log of the absolute value. I could say, since I have a common denominator in there, I could go ahead and combine that and say it's the natural log of the square root of x squared plus 4x plus 7 plus x plus 2 all over the root of 3 plus c. But then you would remember, well, that's just anytime you have the natural log of a numerator over a denominator, you could go in and say, well, then it's going to be the natural log of a minus the natural log of b, In this case, it's the natural log of all of this, which I wrote in my answer. But then I have minus 1/2 natural log of 3 plus c. Well, that 1/2 just came because that 3 was to the was inside of a square root, which means it's the 1/2 power. And you say, well, okay, that constant is there. Now, what Achieve is going to want you to do, there's nothing wrong with this answer. This answer is fine. But if I'm trying to absorb as much of my answer as possible into C, then I don't want to put any other constant in that answer. So it's kind of silly to say, hey, I'm going to subtract 1/2 the natural log of 3 and then add any constant I want. Why not just go ahead and say this can take part of that constant, and the better answer here would just be to say the natural log of the absolute value of the square root of x squared plus 4x plus 7 plus x plus 2. Now, that x from 2 has to stay in there because all of that's part of the function inside the natural logarithm. So you can't, please don't think, well, why don't you get rid of this 2? It's because it's in there with the function of x inside the natural log. It cannot be separated from it. But then that minus 1/2 natural log of 3 can go away, and I just have the plus c there. So my final answer in red there is actually better. Now, the answer I had circled, it is correct. There's nothing wrong with that. But the answer in red is the answer that Achieve is going to want, simply because in the instructions they will always say make sure as much of the constant is absorbed into C as possible. That's how we absorb a constant into C, by just saying, well, there's no sense in subtracting this and adding this. Those are both constants. Why not just call it all plus C? Now, if you're thinking, well, hey, this is looking pretty fun. Well, the fun's not over. What if you don't even have a quotient? Most of our earlier problems were quotients. What if I just have an expression like this, the square root of 12 plus 4t squared? The first thing I'm wanting you to think is, well, hey, why not simplify it by factoring out a factor of the square root of 4? Well, that's what I did. Notice I factored out a factor of the square root of 4. 12 divided by 4 leaves me a 3, and of course 4t squared divided by 4 leaves me a t squared. So then that square root of 4 came to the outside as a 2, and then I'm ready for my trig substitution. You say, okay, anytime you have a variable squared plus a constant squared, you're going to let that variable equal the square root of this number, which is square root of 3 again, times the tangent of theta. Anytime it's a squared plus x squared, or a squared plus t squared in this case, you'll let t is equal to the root of 3 tangent theta. Now I can say, well, yet again also, dt is going to be the square root of 3 secant squared theta d theta. I go down into my problem. This square root of 3 plus t squared is going to be 3 plus 3 secant squared theta, and then I can say it simplifies just like my last one did. The inside portion would be 3 secant squared theta, and then the square root of that's going to be the square root of 3 secant theta. So when I'm looking at this right here, this part, and I didn't show it, I just simplified here, but I'll explain why it's simplified. This part we know is going to be equal to the square root of 3 secant squared theta. So I already had a square root of 3 as a factor inside of this group, and then we had a factor on the outside as well, because the dt became the square root of 3 secant squared theta d theta there. So please notice, you have a factor of the square root of 3 times another factor of the square root of 3. Well, square root of 3 times square root of 3 is 3. Those two will combine to be one factor of 3 that gets brought out to the front, multiplies the 2 for a 6. But then I would have secant to the first times secant to the second is secant to the third. Well, anytime you're dealing with the secant function in there, it's a little bit rough unless you also have a tangent to use a nice identity with. But in this one, I'm just using a reduction formula. So if I say, well, okay, secant cubed theta. Now, if it were secant to an even power, we could work with it. You could say, if it were secant to the fourth, we could break it down into secant squared times secant squared and call the first secant squared 1 plus tangent squared, and it'd work out really nicely. Unfortunately, odd powers of secant, not so nice. So I had to use reduction formula number 48. So if you go to the table of integrals I passed out in class, or also remember it's in the back of your book, I just said that the secant cubed is equal to the formula secant tangent over 2, and I just pulled this straight from the formula sheet, plus 1/2 times the integral of the secant of theta d theta. But then you could say, well, yeah, but there's another one. We've already used the integral of the secant up here for number 13. I really could have said that in this step, the integral of the secant function I'm doing in this one, and I know that the integral of the secant, and you might even have it memorized by now, it's the natural log of the secant plus the tangent. So my integration is done in these two steps. I've multiplied the 6 through here, and I had the 3 secant theta tangent theta, and then plus 3 times the group of the natural log of the secant plus tangent, plus our constant. From this step to this step, we had to go back and plug it in terms of our original variable t. We knew that t was equal to the square root of 3 tangent theta, so t over 3 is the tangent of theta. That means in my trig triangle, the side opposite theta had to be t, the side adjacent had to be the root of 3. So my hypotenuse had to be the square root of t squared plus the root of 3 squared, or t squared plus 3. So then the secant, that's going to be the hypotenuse over the adjacent, the square root of t squared plus 3 over the root of 3. And then the tangent in this problem, obviously we already know, t over the root of 3. We multiply those in there. The 3 cancels out those two roots of 3's in the denominator, and I just have t on the square root of t squared plus 3 plus 3 natural log. Now, notice what I've done here, guys. I knew that this numerator would have both of these terms, the square root of t squared plus 3 plus t, and I knew that my common denominator would be the root of 3. So I went ahead and just said, well, then this is going to be 3 natural log of those terms in the numerator, and then the denominators we would subtract. I subtracted minus 3 natural log of the square root of 3. I could have even said minus 3 over 2 natural log of the root of 3. But now, and there's nothing wrong with this answer, it's fine, but in order to get to an answer on achieve, what you'll want to do is make sure any constant that's possible gets absorbed into C. So the answer that we will do here is t on the square root of t squared plus 3 natural log of that absolute value of the square root of t squared plus 3 plus t. And then that minus 3 natural log of the square root of 3, that just gets absorbed into the constant. We know that that's nothing but some irrational number. Well, that irrational number can just be contributing to whatever the value of C is. And I need you to see that. Now you're thinking, well, okay, is that where the cool problems end? Oh no! One more page. So let's look at number 6 here together. We have the integral of x cubed on the square root of 9 minus x squared, and we're integrating this with respect to x. Okay, so in this problem, I'm doing a sign substitution, and you need to see that. Anytime you have a constant squared minus a variable squared, it's always going to be a sign substitution, where in this case, we let x equal a sine theta, which is 3 sine theta. So the derivative of 3 sine theta is just 3 cosine theta d theta. I go into my problem, and I know I have an x cubed to begin with. Well, if x is 3 sine theta, then x cubed is going to be 27 sine cubed theta. We know that that square root is just going to become the square root of 9 minus 9 sine squared. But please remember, the whole point of that is you know that that inside portion is going to be 9 times 1 minus sine squared, which is 9 cosine squared theta in there, which is going to equal 3 cosine theta. So whenever I see that square root, I need to just be thinking of it as 3 cosine theta. Now, the other 3 cosine theta came from our dx. dx was equal to 3 cosine theta d theta right there. So now I go into my problem and I start trying to simplify everything out. Please notice we had a factor of 3, a factor of 3, and then a factor of 27. Well, 3 times 3 is 9. 9 times 27, 243. I have the sine cubed in there, and then I had a cosine times cosine for cosine squared. As soon as you see that sine cubed cosine squared, you should be thinking, fantastic, because if you have an odd power of sine, cosine, tangent, or cotangent, it can be simplified out. So instantly what I did here is I said, well, I can call this sine cubed theta, sine squared theta, which is 1 minus cosine squared theta, times the sine of theta. And then what I will do is I'll go ahead and distribute this other cosine squared that was on the outside into that group, and I'll get cosine squared theta minus cosine to the 4th theta times the remaining factor of sine theta there. Now at first this may not look better than what we have here, but it's so much better because now I can do a U-substitution and let U equal the cosine function, and we know that the derivative of that is going to be the negative sine function. So the only thing I'll need to do to go from this step to this step is say, well, I didn't have a negative sine of theta, so we could always multiply the inside by -1 if we make sure to multiply the outside by -1. So this problem becomes negative 243 on the integral of u squared minus u to the 4th, and then everything else becomes the du that we had in there, multiplying the inside by negative and the outside by negative. So all of this could become du. Now I can go through and say the integral of u squared minus u to the 4th, that's going to be u cubed over 3 minus u to the 5th over 5 plus c. At that point, it's easy to go back into terms of cosine. I have, it looks like I chose to rewrite it in descending order and say, well, okay, my first term is going to be a positive, and that's why, because I wanted to put the plus sign first, positive 243 over 5, and then I'll have u to the 5th becomes cosine to the 5th, and then the second term is going to be minus 243 over 3. That's going to simplify in the next step to 81. I have a u cubed there, which becomes cosine cubed plus c. Once you get your answer back in terms of theta, you say, now I can get it back in terms of x by using my trig triangle. Our relationship in this problem was that x over 3 is the sine of theta. So opposite theta is x, hypotenuse is 3. The adjacent side is our square root of 9 minus x squared. And again, the form from the original problem always has to show up in your trig triangle. If it doesn't, that's an indicator that you've done something wrong. Okay, but everything is good here. I go back into my problem. Cosine to the 5th theta. That'd be adjacent over hypotenuse to the 5th. That's where this fraction comes from. Cosine cubed theta. So again, that's just adjacent over hypotenuse to the 3rd power. In this step, I also went ahead and simplified the 243 over 3 to the 81. So now, upon simplification, I knew that 3 to the 5th power was 243. That's why that 243 canceled out, and I only had a denominator of 5, and I just left my numerator as the square root to the 5th power. Minus over here, again, 3 to the 3rd power is going to be 27. So you have 81 divided by 27. That's going to give you a factor of 3 out front, times the root of 9 minus x squared quantity cubed plus c. The final problem I want you to see in this section is number 7 here with me. When we look at this one together, you can say, okay, you have the group 9t squared plus 4 quantity squared in that denominator. So the thing that I really was concentrating on in here first is to try to simplify out that group. So you'll notice I pulled that over here to the side and I said, well, 9t squared plus 4 quantity squared. That's the same thing as 9 times the group t squared plus 4/9 all being squared. But then if I have a product squared, then the first term is squared, 9 squared is 81, and the second term is squared, which means I have t squared plus 4/9 also being squared there. Forgot my little square on that group. So now I can say, well, okay, I have the 81 as a factor in the denominator. Notice I went ahead and brought it out front and then said I have the group t squared plus 4/9 to the second. That's where I got all of that from. And this was a necessary step because in your trig substitution, remember, it needs to be x squared plus a squared, or in this case, t squared plus a squared. You don't want a coefficient in front of that term, so I went ahead and got rid of it in the very beginning. So now I can say I can let t equal the square root of this number, which is going to be 2/3, and then tangent theta anytime it's t squared plus a squared. So t is equal to a 2/3 tangent theta, its derivative 2/3 secant squared theta d theta. Once we do that, it works out pretty nicely here. You can say I can plug the dt into the numerator, the 2/3 secant squared theta d theta. The t equal to 2/3 tangent theta. If that's the case, then t squared is 4/9 tangent squared theta plus my 4/9. And from this step to this step, all I've done is I've squared that out. That 4/9 tangent squared theta plus 4/9, let me show up here, it would be the same thing as 4/9 times the group tangent squared theta plus 1. And you know that all of that group is being squared. So then I could just say, well, 4/9 squared is the same thing as 16/81. Tangent squared theta plus 1 is the same thing as secant squared. Secant squared quantity squared is going to be secant to the 4th. So now I have my 16/81 secant to the 4th in the denominator, and I've simplified out the fractions. 2/3 divided by 16/81. I got a fraction for that, came out front, multiplied it by 81, 1/81 to get my 1/24. And then secant squared over secant to the 4th would give me secant squared in the denominator. Rather than having secant squared in the denominator, I went ahead and said, well, that's the same thing as cosine squared in the numerator. And then at that point, we use our power reduction formula, which says that cosine squared theta is equal to 1/2 times the group 1 plus the cosine of 2 theta. So you'll see precisely that's what I put in my next step here. That 1/2 comes out, multiplies the 1/24 to give me 1/48. And then the integral of 1 with respect to theta is where the theta comes from. The integral of the cosine of 2 theta is the sine of 2 theta over 2, or 1/2 the sine of 2 theta. At that point, though, I would just need to simplify and say, but the sine of 2 theta is equal to 2 sine theta cosine theta. You'll notice that's what I did right here. So this 2 sine theta cosine theta, this 2 in the numerator and denominator canceled, which is why I still have the 1/48 multiplying the sine theta cosine theta in this step. And I have the 1/48 times the theta as well, plus my constant of integration. To get this into terms of t, all I needed to do is go back to my original problem and say I let t equal 2/3 tangent theta. So if that's the case, then the tangent of theta is equal to 3t over 2. So I said, okay, the side opposite theta is 3t, the side adjacent to theta, is 2. My hypotenuse has to be the square root of this side squared plus this side squared, your 9t squared plus 4. Now we go into our problem. 1 over 48 times theta. I used this for theta. Theta is going to be the inverse tangent of 3t over 2. And then plus 1 over 48 sine of theta. That's the opposite over the hypotenuse. Cosine of theta, the adjacent over the hypotenuse, where that comes from. As soon as I saw that, I knew these two square roots combined to be just 9t squared plus 4 to the first power. And then my numerator would have been 6t. That's 6t. Well, the 6 reduced down with the 48. 6 goes into 48 8 times. And then I added my constant of integration for the final glorious answer. And this is a case where there is no constant that gets absorbed by the c. Everything else is a function in terms of t in that problem. It can't be separated apart from it. So hopefully this helps you out with the trigonometric substitution. This builds on to our next section, which is my absolute favorite section of the entire semester, integration with partial fractions.